let's look at functions that we have seen to be useful if they are written in terms of an accumulator. And the examples that we had seen so far are reverse, which I've repeated here, and sum, which I've also repeated here. And I've made my accumulators strict. For the sum function, we have seen that this is really necessary to get the behavior we want. For the reverse function, we have seen that it is at least not harmful. I've also included as a third example the length function. The length function counts the number of elements in a list. It is also better written as an accumulator. We get exactly the same problem otherwise as we get for sum if we write it as fold right, as we now know, essentially using the standard design pattern. We get also a right nested chain of additions, only that they're all additions of 1, but nevertheless we cannot reduce any of these additions until we reach the end of the list because they're parenthesized in the wrong way. We really want to initialize a counter and increment the counter by 1 on every step of the way, and again the counter must be forced, otherwise we build up additions of 1 in the accumulator. So the strictness annotation here is also very important. Now the plan is to play essentially the same kind of game as we did before with the other functions, to use these 3 examples as a template for finding out what the common pattern is. I'm just going to slightly rearrange things to make it a little bit easier for us. So at the moment, we always have pairs of 2 functions, right? We have reverse and reverse awks, we have sum and sum awks, and we have length and length awks. And in general, I think this is good. It is good to have all these functions as top-level functions. If we really want to make it clear that reverse awks and sum awks and length awks are helper functions, we could still choose to not export them from our module. That is something one can do. We haven't discussed module export lists, but it is possible without trouble. In general, it's good to have them as top-level definitions, though, because that means that we can individually test them. So I can, for example, still now call some awks with 40 and 5 and 6 and see what is the result of this. And we can see that 5 and 6 are just added to the current value of the accumulator, and we get 51 as the result. Right? We can do these calls. What I'm now going to do, though, is I'm going to make them local definitions by using a language construct that is called where. So I'm just going to move them underneath the other definitions. So now with the where clause, you have to be careful with layout again. So the where itself has to be indented corresponding to the parent definition, and then the definitions that come underneath the where also have to be indented again. Now if I write it like this, then it means that the definition that I make here is only available in the equation that I have defined directly above. Right? So it is a definition that is local to up here. And now if I reload this, I cannot call some awks anymore because it is not a top-level definition, and Haskell will say it is not in scope. And now I'm going to go even further. I'm going to not call these definitions reverse awks and some awks anymore. I'm just going to call them by a common name, and I'm just going to use a relatively generic name, which is go. So I'm going to rename reverse awks to go. I'm going to rename some awks to go. That's not a problem now because they're local, so it doesn't matter if they're all called the same. In fact, it makes these different definitions look more similar to us now. Right? And I'm going to call length awks also go. Okay. And then to save a little bit of space here, I'm going to remove the type signatures of the Go functions. In general, type signatures are a good idea. There is a slightly tricky aspect about type signatures for local definitions sometimes. I may make an optional separate video on that. But for the time being, let's just look at these simplified definitions and assume that type inference, of course, works normally as before. I've just gained a little bit of space here so that I can actually start writing my general function underneath and still have all three examples on screen. So because we've renamed our previous general function into foldr, which is the official name of it, I can start with just the name fun again. And again, I'm not going to use a type signature this time here either, because I want to make use of the type inferencer here. But again, I'm expecting something that in essence has some extra parameters perhaps, but will take a list to a result. So that is again the same thing, right? We are starting from a list and we're going to compute a particular result. And now I'm just going to copy what we have. So we always call go, as you see, and we are always calling it with something which is the initial value of the accumulator. And even though this is now 0 in both these examples, this is really variable in the general case. The initialization of the accumulator really depends on the function that we want to write. And actually, the length function here is wrong. I should have tested this. It should mention the accumulator in the empty list case, right? Actually, if we had 0 there, that's an interesting question, right? What would happen if we had 0 there and if I actually tested this? So then the length function would return 0, right? Because we are computing the length in the accumulator, but then when we reach the empty list, we ignore the accumulator and always spit out 0 as the result. So this really has to be the accumulator. And if we do that, then our length function will give us the right result. Okay. Easy to fix, fortunately. So we always call go with the initial value of the accumulator. And I'm going to give a name, let's say ini for initial, to the initial value of the accumulator. And that will become an argument of my function. Okay, so that is something that is different for all the different examples. Let me bring up the examples on the screen again so that we see them all. And then we now always have a where clause, and we always have go here, and go always takes an accumulator and has a case for the empty list and has a case for xcons access. This is always exactly the same. And even more is the same, and this is different from the situation we have been with the standard design pattern, right? We had the flexibility to initialize the accumulator, but in the empty list case, we now have no flexibility. In the empty list case, that was actually the mistake that I had just made. We always return the accumulator. That's the whole point. The accumulator is the result that we are accumulating, and we want to return it in the end. Okay, so this part is easy. And also the same as that in the cons case here, I always have a call to go on access. There is no variability in that part. That part of the structure is completely fixed, right? It's part of the point of this particular pattern that we are tail recursive, that go in the cons case immediately calls go again, that there is nothing being done with the result of the call to go. The only flexibility we have is in updating the accumulator. And for updating the accumulator, we again have two inputs. We have the old accumulator, right? The acc value that comes from here, and we have the x. Okay, so we make another parameter for our new function, which we call update, and that gets the old accumulator and the x as inputs. And then we make update another argument of our function. And now it works out nicely that we made go a local function. I don't actually have to make update or ini an argument of go, because this update parameter is just staying the same throughout the execution of go. And one of the advantages we have with local definitions is that all the things that are in scope for the equation that the local definition is attached to are in scope within the local definition as well. So we can just use the update function here. And then we see that this type checks and we get an inferred type again. And the type looks actually rather similar to the type that we had before. So now this time, though the numbers are slightly different, so GHC decided to call the list element type T2 now. So let's rename T2 to A again. So our list that we start with is again a list of A's. So we have an A here and an A here. And let's call the result type, this is T1 here, let's call that R again. So we rename T1 to R. Okay. And now indeed, if we compare this with the type of foldl, foldr, let's go up here. We see that it is almost the same. The only difference is actually in the order of arguments to this first function. Here we get A to R, and here we have R to A to R. And actually that is somewhat arbitrary even, because I can decide here in which order I give X and the accumulator to the update function. So I could even have made both functions exactly have the same type. But it is good because they are subtly different functions. It's good if they have slightly different types, I guess, and can be distinguished. And the idea in foldr is very clearly that if we go back once more here up to the situation that we have here, that the recursive result is coming from calling the function recursively on the tail, and the X is the first element of the list. So to preserve sort of the relative order between these two components, that the X is given before the recursive result, so that reflects A to R. And here the idea is a little bit that we are traversing the list from the beginning, and we start with the accumulator, and we're always like taking the elements one by one, right, and updating the accumulator with them. So if we start with the accumulator at the beginning of the list and we take the elements, it's kind of natural that the accumulator is coming before the next element as the input. But right, I mean, this is just a decision we're making. Right, the essence is what's happening within the definition, and that this captures this particular pattern. And this time, because we've already seen the other function before, I can give it away up front that this function also exists, and it is being called foldl prime. We'll get to the prime in a moment in the libraries. And now that we have identified it and given it a name, we can again try to re-implement our existing functions in terms of foldl prime. Okay, so now I do get a little bit of trouble with the space that I have available, so let me rearrange things slightly to make it a bit easier to follow. Let me put the foldl on the top. And here we have our reverse now, and now we can nicely see both foldl prime and reverse, and we can try to write reverse prime in terms of foldl prime. Okay, so This is a function immediately from a list to a result. So I can just immediately say this is foldl prime applied partially to two arguments. Again, if we apply the first two arguments to foldl prime, then what's left is exactly a function that takes a list into a result. And now I can look at my whole types again. So again, the initial value of the accumulator is typically easier. It has to be a list of A's here, and it is just the value that I'm initializing my accumulator with. It's the argument to go. So that's very easy to read off. It is the empty list in this case. And in the update function, right, gets the accumulator and the X and computes the result out of that. So here the order we chose is not helping us. So we get the accumulator and we get the X, and we construct X cons the accumulator. So we flip the arguments around. In fact, flipping the arguments around is a function that exists. So it's one of these nice little helper functions that sometimes are useful. We have seen one helper function that is sometimes useful in the context of pairs, one small function uncurry, right? That was something that we discussed before. Flip is another library function that is defined in the prelude or exported via the prelude actually. Is a function that you can use if you have a binary function in curried style of type A to B to C, and you want to turn its arguments around. You want to turn that into a function of type B to A to C. That is what flip does. And how does flip work? Well, it takes this function of type A to B to C. And now remember again, this parenthesization of functions is right associative. The function arrow is right associative. So here the parentheses are necessary. Here, around this part, they are just for emphasis. Even if I omit them, it still means the same thing. I just wanted to highlight that the way you typically look at flip is that you take a function and turn it into a function again that has its arguments flipped. But we can as well see it as a function that takes three arguments in curried style, namely this function, and then an argument of type B, and then an argument of type A, and has to produce a C. So let's take the B and the A, and then we have to produce a C, and we can do that by calling F with both arguments, but in flipped order, by calling F with A and B. So that is what flip does. And if we have flip, then we can, rather than writing this piece of code here, we can just say, well, we want to apply cons, but in order to apply cons, we're getting the arguments just in the wrong order. We get the accumulator first and the X second, and we don't want to compute acc cons X, we want to compute X cons acc. Therefore, we can just use the flipped version of cons. Now this is underlined because it's a name clash, right? Ambiguous occurrence, flip. So I can add flip to the functions that I'm hiding from the prelude, and because I've just re-implemented that. And this is a version in which I can write it. Of course, the lambda term that I had here first is perfectly fine, right? It's just to introduce you to yet another of these useful little helper functions that are used by people. So if you see it occurring in other people's code somewhere, it's good if you know what it is, and you may very well find it useful yourself, right? So now let's continue our rearranging. Let's move the sum up to directly behind foldl prime so that we can try to re-implement sum in terms of foldl prime easily. So we want to have the same type signature. And again, this is a call to foldl prime with two arguments. The second argument is the initialization, the initial value of our accumulator of type A here, where A is in the none class. So we want to put 0 here because that is our initial value in this case. And here we have our update function, and this time things are working out nicely. So the update function is getting the accumulator and the x, and we're just adding the two things. So here we can really just use plus. So sum is very, very nicely defined, just as foldl prime plus 0. Okay. That leaves us with length. Length is very similar to sum all in all, so we don't expect it to be significantly different. It does not look quite as nice because we ignore one of the arguments, right? And just replace it with a 1. So if we go to length, we bring up the entire code for foldl here. Length goes from a to int, and length prime is again a call to foldl prime with 2 arguments. The second argument is the easier one to fill in. It's of type int. It has to be the initial value of the accumulator. That's again 0, also in this case. And here we get the old accumulator and we get the x. Okay. And then we ignore the x and just add 1 to the accumulator. So we can write this like that. Okay. There are again other ways of simplifying this function, but I'm not going to distract too much from the point of introducing foldl prime here by introducing yet another function. Flip is going to be enough for now. So what we've achieved now is we have successfully rewritten length and sum and reverse all as foldl prime invocations, and we've identified this pattern as well. And here the benefit is even, I would say, slightly larger, right? Because the original definitions are slightly more complicated. They need this helper function or additional function which like maintains this accumulator. Nevertheless, in principle, the same guidelines apply that I've already mentioned for foldr. The idea is that by using foldl prime, you're making it clear to the reader that you're using this pattern, right? Whereas if you spell it out explicitly, you always have to convince yourself that it's really this pattern that is going on, that there aren't any subtle differences. So you make it clear this is just a traversal of a list using an accumulator. But otherwise, again, some functions fit into this pattern extremely nicely. The sum function is an example of this. And all 3 here are reasonably straightforward to write. So if you feel like things become clearer and shorter and more concise by using foldl prime, then by all means prefer it over pattern matching. But if things actually become more complicated or are difficult to squeeze into this pattern, then spell out the definition like this by hand. And just keep in mind that if you're using an accumulator, you probably want to make it strict. The strictness is exactly the reason why this version of fold is called foldl prime and not foldl. So foldl prime is the version in the libraries that has this strict accumulator. Foldl is the same function, and the only difference being that you don't make the accumulator strict. As I've already said, this is basically never a good idea. It is a little bit strange that the Haskell library is actually designed in such a way that the prelude exports foldl without the prime and foldr directly, whereas foldl prime is hidden in the data.list module. So if you actually want to use foldl prime from the libraries, you have to import the data.list module. So there is data.list.foldl prime, which again is generalized to the foldable class. But if you look at this thinking of the T as a list, then you see it has exactly the same type signature as our foldl prime, and it does work in exactly the same way. And really, you have to go to extreme lengths to construct an example where using foldl would be better than using foldl prime. There are some few examples where it is not worse, such as the reverse function. The reverse function can equally well be written using foldl than with foldl prime. But it is almost never better. So really your intuition, your programmers in question should always just be between, like, should I use foldr or should I use foldl prime? Or equivalently, if you talk in terms of the expanded versions, should I directly implement the function on the list using the standard design principle by pattern matching and making a recursive call on the tail? Or should I use a strict accumulator? That's the choice you have to make. And I've been giving you the guidelines before. You use foldl prime in a situation where the operator you're using needs both arguments in order to be reduced, and or where you need to reach the end of the list before you can hope to produce a result. Whereas if you want to have the option to produce a result while traversing the list or produce an incremental result, then you definitely want to use foldr, because foldl, just like the pattern that captures the accumulating argument pattern, cannot produce a result before reaching the end of the list, not even a partial result. In the cons case, it makes a tail call, and only in the empty list case, the accumulator is actually being produced. As a final remark, I want to say why foldr and foldl are being called foldr and foldl. So the folding comes just from this intuition that you walk over a list and you do something with the element, and often that is producing a smaller structure. Not always, right? Mapping is implemented in terms of folding or filtering and produces a new list from a list. But for example, summing the elements up is sort of collapsing the list structure into an integer. So that is a bit like folding the list together. That's the intuition behind the name fold. The L and R are for left and right, and I want to comment on that briefly because I sometimes hear people saying, "Oh, that is because foldl starts on the left and foldr starts on the right." I wouldn't go as far as saying that is wrong, but I think it is at least misleading, because remember what a list is in Haskell. A list is defined in terms of the two constructors, the empty list and the cons constructor. And the cons constructor is asymmetric, right? It always gives us access to the first, or in our view, probably the leftmost element of the list. And then there is the tail, which is to the right. And in order to access the end of the list, you always have to start at the beginning, and you have to traverse the list and go all the way to the end until you reach the rightmost element. So there is no way in Haskell to access a list that doesn't start at the beginning, that doesn't start on the left. So that's why I think saying that foldr starts at the right is a little bit misleading. The better intuition, in my opinion, is to look at what do these functions produce out of a list. If we try to symbolically evaluate a call to foldr with two elements, if we say we have these two operators here, the cons and nil, And we are assuming now we have a 3-element list, let's say, X, Y, and Z, right? And we remember that the list syntax is just syntactic sugar for this, right? Then let's just see what foldr produces. So it's probably best if I copy this to a position where I have foldr on the screen so that we can convince ourselves that I'm not lying. So this matches the second case, right? Because the list is not empty. So I'm going to replace this with cons of x and foldr cons nil of xs, which in this case is y cons z cons the empty list. Now I'm going to make a minor modification here, and I'm going to write cons in infix form by using backticks. We've discussed in the beginning that this is equivalent to writing it in prefix form, but perhaps it makes the point that I'm trying to make a little bit better. So, and now I'm going to do this again. So I get x cons, and I don't care at the moment about sort of the performance. I'm only caring about the shape. So I don't know the definition of cons here in my example. I don't know the definition of x. Perhaps actually this could be reduced, but semantically the order of reduction does not make a very much of a difference. So if I want to show what conceptually comes out of it, I can just continue reducing foldr, and that goes by the second equation again. So then this time I'm getting y cons, I'm again writing it infix, foldr cons nil of z cons the empty list. This. And then I'm going to do this again. And here again I'm getting z cons. And now foldr cons nil of the empty list. Okay. And the foldr call to the empty list ultimately reduces to nil. So if you look at this list, that's the list that we started with. And remember that actually the cons operator is also right associative. So really we can think of it as being parenthesized like this. So then this is the list we started with, x cons y cons z cons the empty list. And this is the result that we end up with, x cons y cons z cons nil. All the occurrences of cons have been replaced with applications of the function cons. All the occurrences, or the only occurrence of the empty list, has been replaced with a call to nil. Right? But the structure of the list is maintained. We start with the right associative structure, which is the list, and we end up with the right associative structure of cons calls, where at the very end, where the empty list was, we have a call to nil. Now let's contrast that with foldl. Right, let's keep this around for reference. Go to where we have the definition of foldl prime. And here I'm now going to not really emphasize very much the strictness of the accumulator, right? It's more about the shape of the computation. So here we start with foldl prime update ini of x, y, z, and again we're going to remove the syntactic sugar, update ini of x, y, z, the empty list. And this is now going to be replaced with a call to go, right? So I get go ini, and here I'm going to assume now, for simplicity, that I'm in this local scope, so that like I can make the call to go, and it means the go that I'm defining here. So I'm calling go ini on this list. And now I'm going to do another call to go, because this is matching the second equation of the definition of go. So I'm going to call my update function on the accumulator. So I get the updated accumulator, which is ini, with x. Okay, and then y comes the empty list. And now I'm also going to choose to write the update application in fix. I can do that. Okay. And then I'm doing the same thing again. So this call, right now, this is the point where we would have to force evaluation of this to the topmost constructor. But nevertheless, I can assume that I've kind of done this, and then look what happens further with the reduction of go. And then again, this matches the second equation, and I'm updating my accumulator again, and I'm getting ini update x. That is the old accumulator I had, and now I'm updating it with y. And then I have set cons the empty list left, and then I'm going to do this once more, and I'm getting ini update init, ini update x, update y, update z, and then I have the empty list. And at this point, my call to go matches line 34, right, the empty list case in the definition of go, where this reduces to just the accumulator, which I can just copy rather than type again, perhaps. Now, if you look at the original list, it's the right associative structure that we start with has been replaced with a left associative call structure, and where we start at the beginning, like at the left, with the initial value of the accumulator, and for every element we make a call to the update function to update the accumulator step by step with each element of the list, right? So, but apart from the names of the functions, the shapes of what foldl or foldl prime produce and what foldr produce are very similar, right? We have x and y and z still in there, but foldr produces a right associative structure where the last element is the nil argument of the foldr function, and it additionally has this property that it completely maintains the original right associative structure, where just the conses get replaced with conses and the nil gets replaced with a nil, with a named nil. Whereas foldl prime changes the right associative structure of the list into a left associative call structure, where the accumulator is initialized in the very beginning and then updated one by one with each of the list elements. So left associative call structure versus right associative call structure, that is, I think, is the right intuition for why foldl and foldr have the names that they do have. I think that concludes nicely our exploration of these two very versatile and very powerful higher order functions on lists. They're probably the most general functions on lists that you get. Of course, map and filter and other functions that we have been seeing are still remaining important, right? But if you have to define something new for which you do not have specific vocabulary now, you can always choose, like, do you want to use pattern matching on the list, or do you want to resort to either foldr or foldl prime to instantiate these standard patterns?